Hello guys, so welcome to our lab 4. In this lab, we're gonna explore, the add instructions. So the objective of this lab is to teach you, if you have some numbers to add together, and the final result will exceed or need more bits than the highest register that you have. Let's assume that the highest register that you have is only 32 bits, for example. So, but the result is more than 32 bits. So in that case, there is a way to do still the addition in which you use, two registers together to hold the result. One register to hold the least significant 32-bit of the final result, and the other register will hold the most significant 32-bit of the result. We're gonna do this with a very simple, example in which we're gonna add these 5 numbers together. These 5 numbers, each one of them is word, is byte. I'm sorry, have a word, and let's assume for the sake of argument that the highest register that you have is 8 bits, which is AL and AH. Let's assume for the sake of argument. Of course, this is not true. Okay. The addition of these 5 numbers is basically, 696, which needs, around 10 bits or more than 8 bits. So it needs one word is sufficient. 16 bits is very sufficient for it. Okay. But let's assume, that, we just have AL and AX. Of course, AX, which is 16-bit, is very sufficient to hold this number. Okay, and we can just, replace these 3 lines with just one line, which is, it will be back at AX and ASI. Okay, and that will be fine. But as I said, here we are teaching you how to use 2 registers to hold, the final result. Okay. This is an example for a bigger problem, we can say. So, in that case, here is the table. This table is a little bit different from the table, that you saw before, because I added here the jump, not carry over. So this, line here, this line has no, register in which you change its value or something. But I want you to report if there is a jump or not. If there is a jump in some iteration, you mark 1. If there is no jump, you mark 0. We're gonna have here 5 iterations. So I want here, to see 5 values, 1, 0, 1, for example, whatever it is. Okay. Good. So let's execute this program, line by line and see how it goes. Okay. So let's run to cursor here. Okay. So at the beginning we have a constant. This constant equal to 5 because we have 5 numbers that we want to add together, and we're gonna put this count into 6. Usually 6 is used like iterator. So after executing this line, CX will be 5. Good. Now we have an array. This array has 5 values or 5 locations, the 5 bytes. So we wanna, point to the first value in the array. So we're gonna put the address of the first byte of data array into ASI. So we're gonna move forward. ASI now has this value. Good. Then we should here, reset both AL and AH. Since we already have, X, which is a combination of AH and AL. Once we do this, both AL and AH should be zeros. No, guys, both are zeros now. Good. Now we first add. Now AL has a 0. Okay. And ESI is pointing to the first byte in the array data. Okay. So we should, after this line here, we're gonna add 0, which is in AL right now, to 125, and the result should be 125. Okay, and 125 is, you know, is 8-bit. When you add 0 to it, it will still 125, which is 8 bits. So there will be no carry. What is in our context here? There is no carry means after the first addition, 8-bit is enough. So we shouldn't add anything in AH. Remember, AH here will have the most significant 8 bits of the result, and the AL will have the least significant 8-bit of the overall result, as we said. Okay, so let's move forward. After this AL should have 125. That's the case. And the carry, look guys, these are the flags. These are the flags of the flag register. And how to show it, basically you right click here and you choose it. If I, for example, if I uncheck, it will disappear. If I check again, it will appear. So the carry after this operation is 0. So we are saying here, jump, not carry. If there is no carry, jump to over, which is the case right now. So we're gonna skip this line and go to over. This line here, line 20. So go, look guys, we skipped that one and we go here. Now we're gonna point to the second operand, second operand basically, or second element in the array 235. We're gonna decrease CX because we already did the addition for one of the numbers. And since the 0 flag is 0, CX basically doesn't reach 0 yet. So we're gonna go back to back. Good. Now in that case, ESI is pointing to 235 and L is 125. If we do this, addition here together, 125 is actually 0, 1, 1, 1, 1, 1, 0, 1. And 235 is 1, 1, 1, 0, 1, 0, 1, 1. If we add these together, this will give us, let's do it from right to left, 0, 0, oh. This will give us 1 here as a carry. And then 0, 1, 1, 0, 1, 0, 0, 0. Okay, guys, there is a 0 here missing, which is that guy here. Okay, so we need 9 bits basically. So what we're gonna do, these 8 bits will go to AL, and AH will take that one. Will take that one means increment AH. That's it, So AH will take that value, AL will take that value, and AH will take this one. Okay, and we are expecting after this addition, the carry will be 1. So let's check that. Just move forward. Look, guys, the carry is 1. Okay. And since there is a carry, this condition jump root carry is not satisfied. So we're going to execute that command here, that instruction. And AH will be 1. Look, guys. And let's check if really, AL has this value, the first 8 bits. So we're going to move back to hexadecimal. Yes, it is, because this is basically 6 in hexadecimal, and this is basically 8. Which is 68 hexadecimal here. Okay. And remember, 125 plus 235 is 360. So if we go back to a decimal, look, AX is, remember AX is, the concatenation of AL and AH. So together, they are 360. Okay. Then we increment ESI to point to 197. Then we decrement CX, it will be 3. And since the 0 flag is still 0, because CX doesn't reach 0 yet, we go back to back. Okay. Now we're going to add 197 to what's inside the L. Okay. What's inside the L now is that 8 bits. These 8 bits. Okay. and we're gonna add to them 197. 197 is basically 1100 0101. Okay, this operation will result in another carry that will go to AH, or added to what's in AH right now, and this result. So again, this result will go to AL, and this carry will be added to that carry. Okay, so after that operation, the carry will not change. The carry is 1 now, and it will remain 1 at what happened. So this condition is not satisfied. So we're gonna increment the H again, and the H will become 2. Okay, then we're gonna increment the ESI, so it will point to the 91, and decrement the CX again. Then we're gonna add 91, and if we do the addition for 91, I'm gonna leave it to you. This will result in 88 H and no carry. So AL will change to 88. So let's go back to hexadecimal. So let's check that together. 88 hexadecimal, and there is no carry. The carry is 0 now. So we will jump basically, and we'll skip that operation. So in here we're gonna increment the ESI, decrement the CX, and jump again to back. And the final operation, we're gonna add 48. When we add 48 to AL, to what's inside AL, this is again 8-bit operation, and it will result in no carry. And the result in AL will be B8. So let's do it. B8. There is no carry. The carry is 0. So we're gonna skip to increment the ESI, decrement the CX, and once we decrement the CX, CX now is 1. So when we decrement it, it will be 0. So the 0 flag should go to 1. Let's check that. It become 1. So that condition now is not satisfied, and we will not jump again, and we will continue to move some AX. Look, guys, and we know that the addition is 6096. So if we do this, sum has let's check. Let's make it decimal, 696. And I want you guys to have the screenshot of the final, after executing this instruction, showing me that sum has 6096. So just one screenshot. Don't take many screenshots. Just one of them, showing me that the final result, that sum has the 696, and show me the the flag registers here and the other registers as well. Okay, guys, that was it for lab 4. Thank you very much for watching, and see you in the next lab. Bye-bye.